So this company, Infotron, makes electronic hockey and soccer games. Now, when I see that right away, I'm thinking we've got two games, I'm thinking two variables. Okay, and then there's some information about each of the games, what's required. And then I come down here and it says this. Just, don't look too hard at this yet. We'll go back and get that. But look at the bottom. It says how many of each game should we produce each day to maximize the total output. So why don't we start here? Why don't we let x equal the number of, say, hockey games to produce, and let y equal ... the number of soccer games to produce. Now, when I set up this problem, I'm going to set it up into a matrix, and in my rows, I'm going to have this. We have hockey games and soccer games. Now, here's how I know to do this. What's my x and y? What am I looking for? I'm looking for number of hockey games and the number of soccer games. These are my categories. So I'm going to put the categories across the top here, and then in the rows, I'm going to put the particular characteristics. And the particular characteristics are, what do you know about each game? There's 2 hours of assembly. There's assembly and testing. Okay, so those are our characteristics. There's assembly and testing. So let's see what we have here. And then this I'm going to write over here as totals. Okay, so what do we know about the hockey games? Each hockey game requires 2 hours labor of assembly and 2 hours of testing. So down here, for hockey, we can write 2 hours of assembly, 2 hours of testing. Now, what do we know about soccer? So soccer, that requires 3 hours of assembly and 1 hour of testing. So this is going to be 3 and a 1. Then what do we know? We have to have something for totals over here. So for totals, what have we got? Well, each day there are 42 hours labor hours available for assembly. So just for assembly, down here for assembly, what's the total hours available? So this is going to be, I'm going to leave a space here, is 42, but it doesn't have to be, we don't have to use exactly 42. We could use less than or equal to 42, right? You don't have to use all 42 hours. And then what do you know about testing? Testing, you have 26 hours available. So that is going to be less than or equal to 26. Now what we want to know here is how many games of each should we produce each day to maximize the total output. So what is the output? The output is the number of hockey games added to the number of soccer games, all right? So it's going to be x plus y, right? X is the number of hockey games you produce, y is the number of soccer games you produce. So what we want to do is maximize the sum of that. So here's our linear program. We want to maximize x plus y subject to, all right, now subject to all this right here. So just write that as a system. So we're going to have 2x plus 3y less than or equal to 42 and 2x plus y less than or equal to 26. And of course our non-negativity constraints. X and y both have to be 0 or positive numbers. So we're going to solve this by graphing because we're in that section. So let's see. This will be number 1. This will be number 2. So let's graph those inequalities. So for number 1, I'm going to graph 2x plus 3y equals 42. So here's my little table. So when x is 0, all right, so put x equals 0 right here. That term goes out and you get 3y equals 42. So y is equal to 42 divided by 3. That is a 14, if I can write it here, 14. And when y is 0, so you put y equals 0 back in here, and you get 2x equals 42, so we're going to get 21 for x. And then for number 2 here, here's x and y. So when x is equal to 0 for that second inequality, you put 0 in here, you just get y equals 26. And when you put 0 in for y, what do we get? So you put 0 in for y here, you get 2x is 26, so divide by 2, you get 13 here. So I'm going to construct the graph now of this system, and to do that, you know what, I think we need a little bit more room, so I'm just going to like magically erase this stuff over here and put my graph right over here. And now I know when I graph, I try to make these axes pretty big. I found if I make them too small that the lines can get mixed up and I can't really see the intersection. So long axis. So here's x, here's y, here's our origin. Look back over here for these y's. I like to do the y-axis first. It doesn't matter, but I just do y's first. What's the biggest y that you have? 14 and 26. The biggest one is 26. So I'm going to put a 26 up there. So that'll be 26. And then where, kind of make a good guess, where would you put the 14? Look, this is all pretty inaccurate. That's why this is not one of the best methods to use. So where would you put the 14? Well, half of 26 is 13, maybe right here. And 14 is just a little bit above it. So I'm going to put the 14 here. Let's do the same thing for the x's. What's the biggest x that you have here? You got 21 and 13. So I'm going to take that big x, that 21, and I'm going to put it out here. So the 21 will go out here, and then the 13, well, the 13, you know, what's half of 21? About 11 and a half, 11. So 13 is going to be over here. All right, so 13 might be there. Now let's draw our lines. So where do these go? The 14 on the y goes to the 21 on the x. So the 14 on the y goes to the 21 on the x. So I'll connect those with a line as best I can. Right there. And now this inequality is, if you follow it up to number 1, that's what we're graphing. This inequality is a less than. So because it's a less than, I'm going to shade the lower left side. So I'll do that right here. Okay, and that right there, that's equation 1. Now let's go to equation 2. That comes from this table here, and the 26y goes to the 13x. So over here, the 26y goes to the 13x. So let's draw that line as best we can. And again, because this is, over here, this inequality is a less than, I know if I run a test point, we're all going to be to the left, the lower left. So we're going to shade this part right here. So where's our feasible solutions? All right, the feasible solutions are in here. Now, optimum values, maxes or mins, occur at corner points. So we have 4 corners. We have this one here, this one here, this one here, and this one here. Now, we know some of these corners. Down here at the bottom left, I'm way at the bottom left at the origin. That is 0, 0. And then I'm just going to come up straight up and kind of go clockwise. What is this point right here? Well, that point is, all right, 0 for x, up 14. Now, this point here, I don't know yet. I'll get that, but I'm going to go down and get this one. This is 13 on x and 0 on y. So this point is 13, 0. This point here, this is the intersection of these 2 lines. Now, the 2 lines are these right here. So I'm going to solve that system. So if you use Wolfram Alpha, okay, I'm going to use Wolfram Alpha to do this. Use Wolfram Alpha, and what you might do is just type in this. You could RREF, or you could just say solve 2x plus 3y equals 42, comma, 2x plus y equals 26. And when you do that in Wolfram Alpha, you come back with x equals 9, y equals 8. So this point right here is 9, 8. Now, we know that the max or min, max for us, right, we're trying to max. The maximum occurs at 1, 2, 3, 4, one of those 4 points. Let's just test them all. So I'll just write a table. I'm going to do it right here. X, y, and x plus y. So I'm going to start here at the origin. That's 0, 0. So if I put in 0 for x, 0 for y, 0 plus 0 is 0. And that makes sense, right? If we build no hockey games, no soccer games, our output is 0. Now I'm just going to put the rest of those numbers right in here. What if we build no hockey games and 14 soccer games, right? That's right here. So no hockey, 14 soccer gives us 0 plus 14. That would be an output of 14. Then let's come down here, right over here, come down here. That point is 9, 8. So suppose we build 9 hockey, 8 soccer. That gives us 9 plus 8, an output of 17, the biggest so far. And then suppose we build 13 hockey and no soccer. That will give us 13 plus 0 was 13. So this right here is our maximum, right? Our maximum occurs right there. So let's answer the question. The question is this: how many of each game should the company produce each day to maximize its total output? So I'm going to answer that question like this. So I'm going to get some room. I'm just going to get rid of this. We don't need that anymore. So I'm going to say that, I'm going to answer everything here. I'm going to say output is maximum when we produce what? 9 hockey games and 8 soccer games. And I've answered the question. There we go.